welcome back to the lecture 10 on inflation, real versus nominal rates and review of financial mathematics for actuaries. Today we are going to study inflation and why money growth is not same as the growth of the purchasing power. Okay, so that's the first goal of this class. In the next we will try to define the nominal rate, inflation rate, which is the new concept for today, and how can we derive the real rate, which we will denote by I prime. And the main goal of this lecture is to connect this real rate, real interest rate, with inflation rate and the interest rate. And then we will give you some tips for between relationships between these I R, which is the inflation rate, and I prime, which is the real interest. That's how we designed our today's plan, and let us review our today's plan. So here the goal of this class is based on to understand the eroding power of inflation, how your purchase power is affected by this. In order to do that, what we are going to do is we are going to define a new concept called real rate. We might have referred to this concept in earlier lectures, but today we are going to formally define this real rate, and then we will contrast it with nominal rate. And then what we will do, we will actually derive the relationship between this real rate, nominal rate and the inflation rate in terms of equation. We will call that equation as Fisher equation. And once we have done this, we will review what we have done in week 2, and we will integrate all the rate concepts that we have studied so far. For reference mapping, this part comes from section 1.7 of Brouwerman and section 9.1 of Chan and Say. For elaborate understanding or detailed understanding on this topic, I refer the listener to read to these sections of the respective books. Okay, so let us begin. So let us start with inflation problem. What is an inflation problem? Suppose I have 100 rupees today. I invest those 100 rupees with 10% interest rate. After a year, I receive 110. So am I 10% richer? The answer is not really, because if the price of bread also rises by 10%, then what I am doing, whatever number of breads I used to buy in last year with that money, I need 10% extra to buy the same thing, same number of breads in 1 year later. Therefore, my purchasing power has not changed. Or we can take an example of a tea, a price of a tea 1 year before and 1 year after, right? So if the price has increased, my purchasing power may or may not have increased. That's the idea, and that is what is the eroding power of inflation. It erodes the interest that you have bought. So how can we set this in mathematical context is the next big question that we are going to tackle. So for that, we need to define 3 distinct variables. One of them we have already studied, which is the nominal interest rate, which is the rate quoted by the bank, and it signifies the growth of your money. Second one that we have is inflation rate. We are introducing it today. This is the rate at which the prices of commodities rise. This is the rate at which the prices of commodities rise. That means if the prices are rising, it's actually decaying the value of your money. So your value of money is brought down by this inflation rate. And then if you have a trade-off between these two, then you can actually study the real rate, which is the growth of your purchasing power. So how much you have grown in terms of purchasing power if the value of money is increasing in your pocket. So how will we understand this, and how will we set the relation between these two? For that, let us take So before going for the next session, actuarial notation for real interest rate may vary. However, we are using real interest rate as I prime. So let us take one example, or let us take one theoretical setup where we will try to derive the relationship. So here we are buying a basket of goods. Okay, so price today is P, and whatever is the inflation, that will make the price of this basket of goods to go higher. As usual, we have our formula, that means in the next year the price of the goods will be P times 1 plus R, because R is the rate of inflation. Okay, so we have understood how price of any commodity or basket of goods is increasing. Now we have our typical money equation, which is money today and money 1 year later, right. So this we have studied well. Now this is what is happening. So how will I compute the real interest that I have gathered, right. So for sake of clarity, let us put this P is equal to 1 and M is equal to 1. So if I have price today is 1, price next year will be 1 plus R, and money today is 1, then money next year will be 1 plus I. This is our standard convention which we use for accumulation function. So if I use that particular relation, then how much is my purchasing power grown? So you look at your accumulated capital. So what will be accumulated capital? 1 plus I is the thing that you are earning, and 1 plus R is the price of any goods unit, of 1 unit of goods that you are going to buy, right. So 1 plus I by 1 plus R. For example, as we mentioned, so I will give you one example. So if you are buying breads, and you can buy, say you have 100 rupees and each bread costs 10 rupees. So you can actually buy 10 breads with 100 rupees. This is today. Now you have your money power, or your money has increased to 110. Okay, so this is 1 year later. After 1 year, okay, so now it's 1110. However, the price of this particular commodity has increased to 12 rupees. Let us, for simplicity, let us not take, let us take 11 rupees. The price of each bread has gone up to 11 rupees. So now in 1110, how many breads you can buy? You can again buy 10 breads, right. So what has changed? Has your purchasing power changed? No, it's not, right. How did I compute that? I have taken this 100, so 1110. So here is the thing, right. So what is 1 plus I here? That 1 plus I will become, okay, so interest rate. So let us first write down the interest rate. What was I here? For the money that I earned, in this case I was, if you look at this, the 1110 minus 10 upon 100, so it was 10%. And what was the inflation that has gone? So I had bread cost to be 10 rupees, now it has become 11 rupees. So that also is actually 10%. Okay. So what I will do, I will put everything here, which is 1.1 upon 1.1, which will give me 1 plus I, which is equal to 1. So this interest I prime, real interest, is 0. I have not earned any interest. The purchasing power has not increased for me. Had it been the case that the cost of bread is now 10 rupees 50 paise, then I could have bought, so it's 10 rupees 50 paise, then for 105 I could have bought 10 breads and I could have spared some money, right. And in that case my purchasing power has increased, okay, and that will be depicted by this. So let us do that calculation all as well. So cost of one bread now is 10 rupees 50 paise, and now I have 1110 rupees. So, I will get 1110 upon 10 rupees 50 paise, which essentially gives me 10.47. So, I can buy 10.47 of the breads, right. That means my purchasing power over a period of time has increased. So, now how will it reflect in this purchasing power? So, what was I and what has happened? Let us look at those things. For example, the bread cost was 10 rupees and now it has become 10 rupees 50 paise. Okay. So, because we are relating inflation on this, I will say the interest accrued can be seen as 10.50 minus 10, which is equal to 50 paise, right. So, this is in that period 50 paise have gathered and this I will divide by 10. So, I will divide by 10 and therefore, this interest rate actually turns out to be 0.05. So, R that I am looking at becomes 5%. The interest accrued remains 10%. Okay. So, in this case what will happen? I will simply substitute this as 1.1, this will remain as it is, and now my new R is 5%. So, it is 1.05. So, I can easily compute and see what is 1 plus I prime. 1.1 divided by 1.05, which is equal to 1.047. 1.047. This according to this equation is 1 plus I prime. So, the real gain will be minus 1 of that. That means, my I prime will be equal to 0.047. So, roughly 4.7% is the actual gain that I have in my purchasing power. This is how a relationship between your money and the basket of goods will be established, and this is a key relation. This actually helps us in having more insight on what is happening to my purchasing power. Am I really growing or not? So, with this insight, let us move forward and describe this as one equation called Fisher equation. So, from the previous slide you can say that if I take multiply on both sides by 1 plus R, then 1 plus I prime is into 1 plus R is going to be 1 plus I. So, let me be clear about this is inflation rate, this is interest rate, and this one is a real interest rate. Okay. This is nominal interest rate, this is inflation rate. Okay. So, with these notations being very clear, I can write the Fisher equation as 1 plus I prime into 1 plus R equal to 1 plus I. Okay. So, once this is clear, then I can actually see is there any easy formulation of this. So, I will do the algebra and I will open the brackets and you can easily see I come up with this relation, which is nominal interest rate is equal to real interest rate plus inflation rate into product of inflation rate into real interest rate. Typically, when we are handling these numbers, these interest rates are in the range of 0.01 or 0.02, say 0.05 and all those things, right, and inflation rates are also in that range. So, when you multiply these two, they go beyond 2 decimals, okay, it is 0. So, in such cases we can ignore this, but this is a approximation. If you ignore that, and then that approximation tells us that your nominal interest rate is nothing but real interest plus the inflation rate. Therefore, if you look at newspapers which deal with finance headlines, they will always give you this approximation that I prime is approximately equal to interest rate that you are earning minus the inflation rate. But this is an approximation, this is not an exact answer. I will make it more clear by giving an example. Right now, if you want to do something in exam, this is the golden rule: I prime plus R plus I prime R. There is no approximation here, it is the exact formula. Okay, so you always remember this and then solve the problem. Okay, so let us use this Fisher equation and try to solve one problem. Here is a problem: a bank offers 8% interest. So now I am not worried about how it is compounded and all. I assume that this is an effective interest rate, 8% interest I. Inflation, which will be annual, is to be fixed at 5%. What is the real rate of interest return, that is I prime, that we have to calculate? We already have a Fisher equation. The Fisher equation says whatever I have 1 plus I, you always remember we always start with 1 plus I to be equal to 1 plus I prime into 1 plus R. This is our Fisher equation. Okay, so now list all the things that are given. R is fixed to be 5%, so it is 0.05. What is I? I is fixed to be 8%, so 0.08. Okay, so now if somebody asks me, okay, then what is the real interest rate that I earn? From the previous slide, you have one straightforward technique, and that technique says I is equal to I prime, because I am interested in real interest rate, is I minus R, right, and this is 0.08 minus 0.05, and therefore this is going to be equal to 0.03. That means I am essentially saying my I prime is approximately equal to 3%. This is that approximation rule that we mentioned on the last slide. If you remember, this is the approximation rule that we mentioned on the last slide. However, we have one exact formula and we want to see that how that exact formula comes into play. So let us look at that exact formula. That exact formula essentially is this Fisher equation. So let us do that one by one. I am interested in 1 plus I prime. So I will use 1 plus I prime as it is. Then I will take 1 plus I upon 1 plus R, right. So I already know this is going to be equal to, with these R and I values, this is going to be equal to 1.08 in the numerator, 1.05 in the denominator, and once this 1.08 upon, you can easily use your calculator and see that this is going to be 1.02857, 1.02857. Okay, so now to compute this I prime, I will subtract 1 from this and I will get the interest rate to be 0.02857, which essentially means it is 2.85%. Okay. And what I got earlier as an approximation, it is 3%, and now when I am computing it exact, it is going to be 2.85%. Let us see our calculations are correct or not in the printed solution. So first is that exact method, 2.86%, okay, and then the approximate method where we are giving the interest rate of 3%. So approximate method always overestimates the return or significantly underestimates the return if the numbers are very big. So based on the inflation rate, we have the estimates may not be correct. So, it is always better to rely on exact estimates, and exact estimates are using Fisher equation, not using the approximation formula. So, in exams if you are asked to calculate, always rely on exact method. Okay, that is the major point here. Let us move to another question. Now, looking at this particular slide, you can think of what will be the case if the inflation rate is higher than interest rate, which is typically the case, right. So, if you look at past few years in India, your bank is offering around 2.5% and your inflation rate goes to around 5 to 6%. What will happen to your real interest rate? Okay. So, that means my money, my purchasing power, is it increasing or not? Okay. So, can the real rate be negative? Okay. That is the question. The answer to that is yes, of course. If inflation rate is bigger than the nominal rate, then your real interest rate can be negative, and it is shown by this example where bank pays 2%, inflation is 6%. So, 1 plus I prime is actually the number which is lesser than 1 and which will give me I prime to be equal to minus 3.8%. So, you are essentially losing purchasing power despite earning the interest on your capital. Okay. So, you should be aware of this trap, and this number real interest rate can become negative. Okay. Okay. Now, we have understood this trap and we have done all these things. Let us now review what we have done with interest rates in last week. So, let us start with week 2 review, which is this. Okay. So, we started with, in week 1 we understood what is effective I, and then we started with variations of this effective I by introducing a frequency of compounding in the first class of this week. So, we established this formula 1 plus I, which is the nominal interest rate, is equal to 1 plus I frequency of compounding m upon m raised to m, and we established various other differences between the real label and the actual interest that you are earning, and the bank add or the real interest that you are earning, and this I always represents the effective interest that you are earning. This IM is the interest on the compounding period. Okay. So, this IM has a name called nominal interest rate. After doing this, we analyzed lot of things with discounting, and we analyzed similar relations as we analyzed for effective I for effective D, and we established a bridge between I and D by using a formula D is equal to I upon 1 plus I. Here the only thing is interest is taken at the beginning if I am discounting, and if I am considering interest rate, then interest is given at the end of the period. So, based on those deviations, we have various similar formulations for effective D. Then we went on and asked, what if these compounding frequencies becoming infinite? The answer to that came with I infinity, which we nominated as delta, and that introduced the notion of force of interest delta, and 1 plus I turned out to be e raised to delta, and therefore body of e raised to delta became ln, and we have delta to be equal to ln of 1 plus I. So, after doing this, we allowed this delta to vary over time, and we introduced the notion of delta t, which is variable force of interest, and we derived analytical relationship between the accumulation function and this delta t, and we saw how to calculate effectively given delta t what will be the accumulation function and vice versa. So, this is our map. In between, we actually established an hierarchical relationship between various interest rates and how is the positioning of delta based on those various interest rates. For example, or a standard investment where interest rate is greater than 0, we have analyzed effective versus nominal interest rate and shown that as your frequency of compounding increases, you require lesser and lesser interest rate. And where did it terminate? It terminates for that infinite frequency where the frequency of compounding is infinity. We got that result to be equal to delta. What happens to the discount? The exact opposite story happens to the discount. So, when we are looking at discounts, this delta becomes the upper bound, and as the frequency of compounding decreases, we are reaching to that final effective discount. So, D12, D4, D2 and so on. In between, the order relationship continues, correct. So, we have these two crucial relationships, and how delta is located at the balance point of interest rate and discount rate is also shown in this particular week. Then finally, we assuming interest rate or the inflation rate, assuming inflation rate is greater than 0, we have shown that our I, which is the nominal interest rate, is always going to be greater than I prime, which is real interest rate, which we have shown using Fisher equation. And now we have covered enough concepts. So, we will reveal some exam traps that are possible. So, first is unit check. While solving the problems, you should always look at the units for which the interest is given. So, if you have effective interest rate I, it should be given per year. If you have compounded interest or which is given with a compounding frequency m, then you will have per period interest. It can be in months, it can be in days, it can be in hours, but per period is very crucial. After that, if you have force of interest, this force of interest is instantaneous rate. So, it should be given per instant, and after that you should give n, which is the number of periods, and that number of periods must match with rate units. For example, if number of periods are given in days and your Im by m is in months, you may compute everything wrongly. So, always n must match the rate units. That is the main idea. And then if you look at this compounding frequency like I12, this 12 generally represents months, right. So, it is a annual compounding which is done monthly. So, n must be in months. So, now we will have a small week 2 challenge, which is example 2. If I have been given force of interest delta to be equal to 10%, can I convert it to quarterly discounting? The answer is yes. So, what are the steps involved? First step is I want to link this delta to 1 plus I, that's the main goal, right. So, let us link this delta to 1 plus I. We already know it is equal to e raised to delta t. Here delta t is 1. So, 1 plus I is e raised to 0.1, and that turns out to be this. Now, you will appeal to this 1 plus I and equate it to discounting factor. So, that relation is very crucial. So, your 1 plus I will be equal to 1 minus what is the frequency of compounding, D4 by 4, and now the most important thing is this is raised to minus p. So, it will be raised to minus 4, that is the most important thing. Then everything is very easy. You take this number and you just substitute it here, you get this, okay. So, this is our step 2. Once you have done step 2, more or less everything is clear, then it is a job of a calculator. You have raised to the power minus 4. So, you will multiply by this number raised to the power minus 1 by 4. and that will give me, if I multiply both sides by minus 1 by 4, this will become 1 minus d4 by 4 is equal to this, which means I have to take 1.10517 raised to minus 0.25, which can be done on calculator, and once I do this on calculator, I will get this answer. 0.9753 is equal to 1 minus d4 by 4, and then it is a standard juggling of numbers from left to right. d4 by 4 you add on both sides and subtract 0.9753 from both sides, then you will come up with this equation, which you will multiply, so that you will get d4 multiply by 4, so that you will get d4 is equal to 4 times this. So finally what you get is the conversion rate of 9.88%. This is the discounting factor that we have derived. Okay. So now we have covered roughly everything. So let us summarize what we have learned today. First, we introduced the factor of inflation. Based on the factor of inflation, we derived Fisher equation, which actually relates three critical components: one, nominal interest rate; second, real interest rate; and inflation rate with this relation. So that is covered. Then what is a real interest rate? Real interest rate actually measures the growth of your purchasing power. If it is positive, your purchasing power is increasing. If it is negative, your purchasing power is decreasing. And we have shown two typical examples of each instance. Then we also learnt that there is a shortcut method for analyzing interest rate or real interest rate, and that gives us a very crude approximation. For example, we ignored the term I prime R, product of I prime and R, and then we derived the approximation I is equal to I prime minus R, and therefore a shortcut way to understand this I prime, that is real interest rate, is I minus R, and we saw the limitations of this approximations as well. So it may overestimate or underestimate depending on the value of R that we are choosing. So in week 2, whatever we have done so far, we have designed a complete toolkit for measurement of interest. What are the tools in our arsenal? I, which is the interest rate, effective interest rate; D, discount rate; delta, force of interest; R, inflation rate, and based on this we have compounded interest. So that those are IM, DM, right. So one is compounding interest rate compounded with frequency M, one is discount rate compounded with frequency M. So what we will do next in week 3, we will actually use these equations and derive equations of value, where we will understand the rates, we will apply them to complex cash flows, where we will deal with loans that involve drop payments, or we want to find exactly the time weighted rate of return of on our money. So all those things we will do in week 3, which will be the most interesting week. So I hope to see you in the next week. Let us learn together. Thank you.